Dr. Guoxin Fang. Guoxin, are you with us?
Yes. Yeah.
Brilliant. Thank you.
Screen,
yeah, originally we wanted to have Professor Charlie Wang from the University of Manchester, but he had an emergency. So Dr. Guoxin Feng from the same lab is going to present some of their outstanding results on the optimization-based geometric computing for deformable structures. So Dr. Guoxin is going to join the Chinese University of Hong Kong in a few weeks, I think.
Yeah.
So congratulations on that. So floor is yours. Go ahead, please.
Thank you. Yeah, can you see my screen?
Yes.
Yes. Thanks a lot for invitation. This talk is supposed to be presented by my supervisor, which is Professor Charlie Wang. So Professor Charlie Wang is chair of smart manufacturing in the University of Manchester, and I'm now currently postdoc research associate in the same group. And today we're going to present some of the work that we've been done in the past 6 to 8 years. So we are working with those geometry-based computing with optimizations for controlling design and for sensor-based perception of those deformable structures. And many of the applications.
You are on mute.
Yes.
Okay, brilliant. Thank you.
Yeah. So in the past few decades, in the past few decades, we see the revolution of the robotic systems from the rigid robotic arm, which show perfect precisions using those rigid links, and we see the compliance being invited into robotic body to build those compliant structures. And then we see the invite of those compliant structures as well as those soft materials into the robotic system. So we build soft robots as a deformable object, and it have different kinds of actuation can driven those soft objects, which including like cable-driven soft hand, like what I show here. And we also see the electrical-driven soft robotics being developed. And this idea is also shared together with the 4D printing community. And we also see the numerical driven one, which is using the compressed air to driven those deformable structures. And also we see those magnetic driven soft robotics. So as a review papers being published in 2015 in Nature journal, we define those materials which have Young's modulus less than 10 times 9 Pascal as the soft materials. And for those robotics or the object being fabricated with soft material, we call it soft robotics. We now see many of the promising applications of soft robotics as a deformable structures, which including in the industry, it can adaptively grasping those industry product, and also it have the abilities to cross over those narrow regions for confined area detections. We also see it being applied into medical applications like for rehabilitations and medical treatment, and also because it can safely interact with the environment, we see those local motion based software robot being developed. This is definitely a new area, and there's many of the challenges for deformable structures, which included the first one is definitely at this time point, we still kind of lack of rapid design tools. We are lack of very efficient but rapid but precise modeling tools that can predict the behavior of the soft robots or the 4D printing deformable structures that we design. Therefore, once we lack of those design tools, we need to build novel algorithms that to control those soft robotics in terms of, but also consider their soft materials inside. This including we need to develop novel sensing technologies to realize the perception and also perception of the soft robotics, as well as we need to develop the novel planning method in contrast with those conventional rigid robotic arm. And also, we need to develop a new method to fabricate those soft materials, and as what we already hear many of the professors being presenting today, using 3D printings for those deformable structures. So our work was focused more on the first two parts, and today I'm going to talk about how we develop and reliable soft robot simulators based on geometry computing, and how we're gonna to using it by incorporate with machine learning technologies to better control and better do sensing-based perceptions as well as design of those deformable structures. Yes, so as I mentioned before, so compare with the conventional robot, soft robots as a deformable object actually presents large degrees of freedoms in the deformations, but is actually controlled by less degrees of freedoms in the actuations. And this shows how we define the kinematics in soft robotics, and as well as controlling those deformable objects. That the forward kinematics of it was actually coming from the actuation parameters to the configuration space. So for soft robots or the deformable objects, the configuration space has been defined probably sometimes become the entire the body shape, which means we try to control the whole shape of the deformable object, which is quite a challenging task because sometimes it can contains like infinite degrees of freedoms. And of course, for robotics application, we sometimes focus on the task space control, which is we only focus on control the end effector positions. But we claim that for soft robotics, we are also very interested in controlling the configuration space. And the inverse kinematics is the inverse direction of this control, which is if we have the target shape or target positions in the task space, how are we going to control those deformable objects by calculating a proper actuator parameters so that we can reach our goal. So why configuration space is so important for soft robot? Because this is a deformable object that really can interact with the environment. For example, when we do the local motions, we need to know how it will interact with the environment so that we can do collision avoidance. And also when we apply soft deformable grippers to grasp something, it's actually sometimes using it in body deformations to reach this tight grasping goal. And of course, when it's coming to the confined areas, it's not a very intuitive way to predict the shape of it and to do a really nice motion planning of it. So our first work is developing a very efficient modeling tool for soft robotics. So at this moment, there are 3 different categories of methods being used. One is analytical models, which can sometimes be very efficiently calculated, but it can be less effective to predict the whole body shape of the deformable object. And so our solution is based on numerical simulations, which can easily get the whole body shape of it, but sometimes it can be less effective in terms of computational efficiency. We also see learning-based model being developed for modeling the behavior of those methods, and we also incorporate this learning those data-driven methods in our research. And once we have the modeling tools, we can do a lot of things. Here I list 3 of them. The first one is we can directly verify analysis, novel soft robots or deformable object designs. And secondly, we can build model-based motion planner and controller so we can get a more precise control of those deformable objects. And thirdly, we see in the many of the nice related work being developed, we can apply those modeling tools to generate a lot of data in virtual space so that it can guide the design and the optimizations in the physical space. And we bring the idea called sim-to-real transfer learning in our research as well. I will mention this later in this talk. So in terms of building effective numerical simulators for deformable objects, we actually have different solutions, including analytical solutions and numerical solutions. So currently, people are using commercial FEA software a lot, including Abacus and ANSYS. However, the main difficulties to apply and sometimes can be really year-defined problem is because for those soft material fabricated objects, we can meet with certain level of nonlinearity in the solving system. This including geometry nonlinearity, which means we can meet with a very large deformation or rotation transformations in the body itself, which makes the system really hard to be converged. And secondly, the material nonlinearity, particularly, especially for the hyperelastic properties exhibited on those softer materials, make the system even harder to be well defined. And also we have actuation nonlinearity, which includes sometimes the force driven by cable or the pressure driven by fluid is really hard to be defined as a clear boundary conditions into the finite element analysis. So target on those challenges, we developed a soft robot simulator by geometry computing. So here we mainly focus on the geometry change inside those deformable object system. So here I have 3 examples. On the left side is a cable-driven soft robot. We can see that the actuations applied to those deformable materials is actually driven by the cable shortage of those red regions that I highlighted here. So this is actually driven by a geometry defined parameter, which is the edge length. And secondly, in the middle part, we can see this is a DA-driven soft robot, and this kind of shape is also being studied in 4D printing or the self-assembled robots a lot. We can see that it's actually when the electrical being applied into the center part, the area of that region will shrink. So this is also being considered as a direct geometry change inside those deformable shape. And also on the right side, we see this is a numerical driven soft robot, and we actually pumped air inside, and it will bring the expansion in those chamber region. So this is also a geometry defined actuation parameters. So our thought in the first place for this simulator is, if we can modeling all those actuation boundary conditions as geometry change, then we can directly mimic the geometry defined elasticity energy so that we can build a fast and reliable solver for those deformable objects on the general kinds of actuations. So this is how we do it. We get the idea from these papers in the computer graphics area, which define the elasticity energy, which directly compute the pure shape change in the element. And then we build those actuation constraints also with the geometry-based change. And then we solving those system as a quite large linear system as convex optimization problems, which turns out to be very efficient. I will show the result later, and here I would like to highlight we also incorporate those nonlinear material properties inside by shape blending. So the idea is for the rigid materials, it will have a more ideal opportunities to protect its own shape or its own initial shape once the loading being applied. And if it is a very soft materials, then it's less effective to protect its shape. So we can having parameters to blend those shape from very rigid materials and extremely soft materials. And we also extend it into the hyperelasticity models by using the physical-based calibrations. So here is physical-based calibrations to mimic the real physical behavior between 2 soft materials. We show that a high efficiency in predict those material bar print with 2 materials. This is by 3D printings, and also we can successfully modeling the twisting behavior of those material bars. We also extend it into the hyperelasticity materials by inviting the nonlinear term. This is we using 3rd order models to fit those shape parameters so that we can also better mimic the hyperelasticity materials in our simulator. So here, let's show some of the results. So our result is really fast. It's around, for these numerical driven actuators, it shows 46 times faster than the conventional abacus finite element analysis. And also by compare it with the existing work like from the SOFA. So SOFA is also a multimodal framework for the deformable object simulators. We can still obtain a quite stable and we can better mimic the physical performance of those numerical driven actuators. This is because so far is based on time integrations, so the error will accumulate during time step. But however, instead, in our simulators, we directly solving the large convex optimization problem, so we can achieve like a one go or the one-shot optimizations to get those shape. Here I also show those DA-driven soft robots. As you can see, we can best mimic the physical performance compared with those physical performance of the actuators. And then we saw that for those deformed objects, because it have the nature of the softer compliance bodies, it actually can benefit a lot from the interaction with the environment, with humans when working together with human robot interactions. It can also benefit a lot from the self interactions. For example, for these chambers, due to the fact that this can have self interaction between chambers, that actually can perform a more efficient deformations. So here we invite two constraints into our optimization pipelines, which is to tackle all of the elements should be free of self collisions, and also we invite define the force equations, which is considered collision free with environment obstacles, and we invite two of the methods to make the collision checking be more and collision response of our simulator more efficient. This including faster collision detection based on ABB tree, which I showed here, so that can very efficiently know which part have the collisions with the environment obstacles, and also how it will have self collisions. And also we invite those spring-based elements to help incorporate and solving the system more efficiently for the better collision response. So here I would like to show some of the results. So as you can see here, our simulator can convert very fast in terms of those very special case. So this is a soft robot grippers that being deformed. Then we using a cube to push it being up, and then it was being expanded more. So if we're using traditional conventional FEA simulators to do this kind of job, it actually takes quite a long time because the system is really hard to be converged. However, in our case, we can reach the whole pipeline in around 2 minutes and 27 seconds, and this is actually a system contains a certain like 79 thousands of tetragens, which is considerably a relatively large system to be solved. And also here, I would like to highlight, we also test the performance of our geometry-based simulators with the 4D printing. So this is the some of the preliminary results we recently developed. So the idea is to print those unstretchable materials into those pre-stretched fabric. So we first stretch those fabric by like 150% of its initial length. Then when we print those unstretchable materials on top of it, we after release those preloadings, it will directly bend back. So this shows how we can simulate those systems. So on the top side is the one element, and on the bottom side, we show how we can put like multiple of those elements to the systems. So these simulators can really help not only the soft robot, but also can be invited into those 4D printing communities to solving the design validations and have the potentials in the future design optimizations. So here I would like to recall the kinematics of robotics. So once we have those very efficient simulators, we can actually, based on these simulators, to solve the inverse kinematics problems, which is if we have the body shape or if we have a target and the effector positions, how we going to compute those actuation space. And here I would like to highlight for the deformable object, since it will interact geometrically with the environment, sometimes no matter if it is analytical model or numerical model or data-driven models, once the interaction being loaded on those soft materials, it will directly lose its precision. So the sensors is not is very necessary to be added into those systems in terms of to adding another load independent signal feedback for the control and the design of those deformable models. I will mention this later. So here including so here we show how we're gonna use in those data-driven method to design a neural network so that we can control the tip positions of these soft robotics to rotate through those very complex curve structures. And we invite if we direct using those numerical simulators inside the loop, we can see that the tracking error is actually quite relatively high. And then we invite sim to real transfer learnings, which is we first generate a group of data in our simulators, then we can directly transfer into the real physical environment by using those we called eliminate the reality gap. So it can have the final result with very less tracking errors. And here I would like to show some of our recent work on using the sensor-based things for the perception of the deformable object. So here we can see we put those sensors. This included the spring sensors and the IMU sensors inside those deformable grippers. And then we applied we applied machine learning pipelines to first generate a group of data by our fast simulators. Then we apply those sim to real transfer learnings so that we can achieve a very precise predictions of the soft robot's performance in the physical world. And the good things about this, about inviting the sensors inside the whole systems, it can stay very stable even on the very large loadings. So here we show if without loadings, it can precisely predict the shape of those deformable objects. And then once we add some of the loadings, like this is the object with 35 grams, and all the way until cola, which have the 50 grams. So I would like to highlight that the whole system is actually around 2 kilograms. So this is quite precisely controlled. And also without by using those load independent perceptions realized by the sensor-based feedback, we can also achieve closed loop control of it. Yeah. And next project I would like to show here how to using those numerical simulators into the design of those deformable gripper is in this project we try to optimize the design parameters, which is being parameterized for the softer gripper designs. The goal is we want to mimic the out of plane stiffness, which is when the softer gripper was interact with the environment, it will slightly shipping to the out of plane side of the models. So this is quite a high non-convex problem to be solved. And so our solution is to generate a group of data by our simulators, and then we fit a continuous design space by machine learning. And so here we apply the RBF functions for that, and then we can directly search for optimization solutions in those continuous design space. So the result is quite promising. So as you can see here, the optimized design can sustain a higher load in terms of heavy loadings being intact here, which means it have a better opportunities to put into the real applications to tightly grasping the objects. Yeah, and one final project I would like to share here is about the design of those soft robot mannequin systems as a very nice applications for the garment industry application. This is a project funded by EPSRC. So what we did is we put those deformable chambers into the mold, like to mimic our human body shape. So because we have the simulators, we can always validate our designs, and we can do the optimizations of the chamber placement areas, and also we can achieve a very high. Yeah, here we shows how the chambers will deform. And by put those chambers inside those soft mannequin designs, we can, yeah, this is the assembly pipelines. Yes, and we're using the vision-based systems for the feedback controls. So we're using scanner to project those data so that we can, yeah. So consider we have a target shape and we can have a captured shape. So by iterations, this is also driven by the simulators that I just present before. We can always, like once we get a target shape of our humans, we can let those soft robotic mannequins to deform to this shape. So this is quite important for the personalized garment fittings, as well as for those bespoke fabrications. So consider we can have those mannequins inside the manufacturing companies, and in the fashion store we can scan the human body shape, and then we can immediately have your bodies in those factories, so it can perfectly fit with your bodies. Yeah. So I give some conclusion remarks. So I present in our previous work, we have developed a very efficient and also precise and general geometry-based direct simulators for deformable structures simulations. So this can be done for both soft robotics and also for those geometry-driven 4D printing and the self-assembled applications. And based on those high efficient simulators, we have done inverse kinematics controls, motion plannings, trajectory optimizations, as well as the design optimizations of soft robotics. This is also, we benefit a lot from the data-driven method, which is the learning-based method. And also we would like to highlight the powerful of the sim-to-real learnings that really help us not only reduce the data that's used for those learning-based methods, but we can eliminate the reality gap between the simulators and the physical environment. We also working on a lot of future directions, which including how we can tailor-made the deformations, how we can customize mechanical properties inside those deformable objects, and how we're gonna to use in those geometry-based computing to control the dynamics for deformable structures. So here's how Professor Charlie Wang would like to thank for all his PhD student collaborators and all the funding source, including EPSRC and the University of Manchester. And as a final remark, the simulators that we developed is open source, and we have two versions of it. And here is the QR code of it. So the first one is the soft robot kinematics control. This is including both simulators and also the inverse kinematics algorithms to control the deformable object. And the second one is integration from my colleagues, and this including the collision with environment as well as self collisions inside of simulators. So yeah, thanks a lot. And if you have any question, please, you are welcome to contact my supervisor, Professor Charlie Wang, or you can send me email. Yeah, here. Thanks a lot. Thanks for the questions. Yeah.
Thank you so much, Guoxin. We enjoyed a lot, and we learned about what you're doing in the University of Manchester. So, would you like to take some questions, or you prefer answering by email?
I can answer some quick questions.
Brilliant, thank you. So we have I think 1 or 2 questions in the meeting chat box, and Frederick is asking about the syringe, the place of the syringe pumps to control the mannequin.
Yes. So that is a very tricky question. So the design of where to put those actuation chambers is actually needs a lot of effort. So in our group, we are mainly taking two objects in the designs. So one is how our human bodies will deform. So basically, we analysis a group of data that is captured by commercial companies, including thousands of human body shape. We do PCA analysis, so we know where our human body will deform or vary the most in terms of the shape. And also we collaborate with fashion industry, so they know better where our human bodies really take into account of those dimensional difference. So we mainly take these two objects into account when we design the chambers and for those syringe placement.
Brilliant, thank you. And regarding the space of the syringes, the contouring system and the mannequin itself, seems like you're using a lot of space for it. What do you think about when it comes to the application?
Oh, okay. Yes, for the syringe system, because this is our first trial, we also now developing micro pump based systems. This is more like a compact equipment. But I would like to highlight that using the syringe is actually a more reliable way, although it's maybe not easy to provide a rapid shape change. Yeah. And the idea is using the syringe system, we can put it far away from those mannequin systems. So the mannequin itself can become electrical free. So you can put it in some regions that really have a lot, like a medical environment with MRIs. Yeah. So using the syringe also have its own advantages.
Okay, great. Or you can use the micro pumps, very small, tiny things
Yes.
embedded
Yes.
inside the mannequin. Okay, brilliant. Thank you. Any other questions? You can also raise your hand if you have any question.